Every leaf that falls never stops falling. I once thought that leaves were leaves. Now, I think they are feeling in search of a place. Someone's hair, a park bench, a finger. Isn't that like us, going from place to place, looking to be alive?
Math is beautiful.
Wait, aren't you the physicist?
And you're the mathematician.
Oh, I see that you're enjoying the Mandelbrot set.
Yeah, I've been thinking about zooming in as a series of choices. And depending on the choices you make, well, you end up with a different picture. How can a whole journey be contained in a single point?
Sounds like you need to find a good book on dynamical systems.
What's that?
It's the field of math that studies anything that changes according to a given rule.
Mathematicians really are something. One name for anything that changes?
Yep, that's right. They say that mathematics is the art of giving the same name to different things.
So, a function that we can iterate and a cup of coffee with some milk in it. Those are both dynamical systems?
Yeah, isn't that cool?
Yeah. You know, it makes me think of something. A poem I read on the subway. It's called Passage.
Oh, what's it about?
It's about leaves.
No.
Well, it's about everything, really.
I mean, isn't that how poetry always is?
I don't know. I don't really like poetry.
Oh.
Now I think it's about dynamical systems. You see, everything is made of the same stuff, and it's always swirling around and mixing.
Like milk and coffee.
Yeah. And the more that I think about it, the more that I see the same behavior in everything. Fran, I really mean everything! Like water. Water's constantly swirling and churning and dissolving whatever it can. Every day, the trains, they fill up with people and they run across the city and mix around, exchanging ideas and stories. What are our heads other than a vast tangle of ideas?
Jeff!
This is interesting. Mandelbrot. Whoa, where are we?
We are in the void. We can think here without any of the distraction of the real world.
But wait, are we in your head or in mine?
Don't worry about it. Your train of thought is on the right tracks, but you need to slow down. If we want to understand a complex dynamical system, it's best to think about a simple system first. Let's look at an interesting dynamical system which is easy to define. We start with a circle.
A circle?
Yep. Before we label anything, all of its points are identical. Let's pick a single point and call it 0. And then we can label all other points by the angle that they make with 0.
Wait a minute. Isn't the angle of that point 180 degrees? Or maybe pi radians? I've never heard of an angle of 1/2.
Well, you could use whatever naming scheme that you like, but there are good reasons to measure our angles in full turns.
So, after traveling one full turn around the circle,
We're back to where we started. Now that we have our space, I can tell you about the rule which makes this a dynamical system. We send each point to the one which is twice its angle, and we call this angle doubling. When we look at all of the points in the upper semicircle, the angle doubling map will stretch them out to cover the whole circle, and the same thing happens with the lower semicircle.
whoa, it's a lot to think about all the points on the circle moving all at once.
It'll help to think about something physical. Let's return to the real world and look at a hair tie.
A hair tie? How do you keep doing that?
That's right, a hair tie. A hair tie is a great way to visualize an angle doubling map. Have you ever used one of these?
Sure. You know, I grew my hair out in college.
Whoa, do you have any pictures?
Right? so we don't have...
No, tell me about the hair tie.
Okay, so everyone knows how to make a hair tie tighter. You just double it up. You start by making a figure 8, and then you bring the two halves together. And if we stretch it out to be the same size as the original hair tie, then we'll have stretched it by a factor of 2.
And that's just what we saw earlier, right? Each half of the circle gets stretched to fill the whole thing.
Yeah, that's right. And what we want to investigate is iterating the math. So applying it to the circle over and over again.
But you can only double a hair tie a couple of times before you reach its limit.
Ah, but that's the beauty of math. We're not restricted by the physical world.
We need to go back to the void.
Now that we understand the dynamical system, we can start to study it.
Well, what questions should we try to answer?
It's up to you. You have to ask the question and answer it.
Well, let's think back to what got us into all this. A leaf travels through the world, and we can describe its journey by listing what it touches. Someone's hair, a park bench, a finger. Let's pick a point on the circle and see where it goes as we double.
What you're describing has a name. That's the orbit of a point. What point should we look at?
Let's try a quarter. Quarter goes to a half, half goes to 1.
Which is the same point as 0.
And then twice 0 is 0.
Yep, 0 is a fixed point of the angle doubling map. When we double 0, we don't do anything at all.
That's easy enough.
When you move on to studying other dynamical systems, it's always a good idea to understand their fixed points, or equilibria, first.
And for the angle doubling system, 0 is the only fixed point.
Which is one of the reasons we are starting with this dynamical system. Let's look at the orbit of another angle. How about 1/5?
Sure. 1/5 goes to 2/5, 2/5 goes to 4/5, 4/5 goes to 8/5. Oh, hang on. I thought our biggest angle was 1.
Well, we've decided to use the numbers 0 to 1 to label our angles. But just like on a clock, we can keep on counting as far as we like, but we will always return to the same place.
Okay, so that means that 8/5 would be the same angle as 3/5, and we can continue doubling.
Yep, and when we double 3/5,
Now we're back where we started. 6/5 is the same angle as 1/5.
it took us 4 steps to get back to where we started, so we say that 1/5 is a periodic point of period 4. There's another kind of orbit that we haven't seen. To see an example, let's look at the orbit of 3/20.
Okay.
Right.
Ah. I see. We still end up in a loop, but it never returns to 3/20, where we started.
Points with orbits like these are called pre-periodic. Let's review the 3 kinds of orbits we've learned about so far. We have terminating orbits, periodic orbits, and pre-periodic orbits. And now, a natural question to ask is which angles fall into which categories? Do all angles fall into one of these categories?
Okay. Maybe we can start by thinking about the orbits that terminate.
If an orbit terminates, then it must terminate at 0, our only fixed point. Let's walk backwards from 0 one step at a time to list the points with terminating orbits.
All right. We know that 1/2 goes to 0 and a quarter goes to 1/2.
There's another angle which goes to 1/2. It's 3/4. In fact, if we take any angle and add 1/2 to it, we get another angle which will end up at the same spot as the original one after doubling.
And that's because a half times 2 brings us to 0.
Yep. With this reasoning, we can see that every angle has 2 pre-images, or points which map to it under doubling.
Okay, I think I can fill in the rest of this picture now. And there seems to be a really nice pattern with the denominators.
Well, now we just need to figure out which angles are periodic and which angles are pre-periodic, and we've classified all the orbits of the angles of the circle.
Not so fast. We have examples of these 3 kinds, but that doesn't mean that there aren't more kinds of angles out there. Can you think of another type of behavior that an orbit could exhibit?
Well, if it doesn't terminate, and it never repeats itself, then it must go on forever without repeating. Hey, like the hat tile.
What kind of angle or number do you think would do that?
It must be an irrational number. Irrational numbers never repeat themselves.
But what is it about an irrational number that never repeats?
Oh, right. It's the decimal expansion of an irrational number that never repeats. But what would the decimal expansion of a number have to do with its orbit?
Aha! What does the decimal expansion of a number have to do with its orbit? Let's look at another example to find out. I think 1/19 is a good fraction. Don't you agree?
Yeah, beautiful. Hey, these strings are starting to make a neat pattern. I wonder what it looks like when we add more and more lines.
Jeff!
Sorry. Getting distracted again.
This orbit is so long. We need to take it off the circle in order to see it.
Okay, I'll help untangle it.
Okay, I think maybe this goes right here.
Get this under
This
that.
one. Oh, this
Pull
one's all
that
tangled
through
up.
the...
Ugh. It's so much harder with all the labels. I think I'm just going to start tearing them off.
Oh, wait, don't do that. How are we going to know the whole orbit without the labels?
No, trust me. We don't really need them. We're not losing any information without the labels, as long as we remember whether the point was in the top or the bottom half of the circle. I've secretly been indicating this with these purple and green beads. Once we take off all of the labels, this particular sequence of purple and green completely distinguishes the orbit of 1/19.
Oh, so that's what the beads have been for. I'm still confused about this color coding, though.
Okay, let me explain. We can color the top half of the circle purple and the bottom half green. And as we calculate the orbit of any point, we will add a purple or green bead to a string, depending on whether the point lands in the purple or green region.
So you're telling me that any number can be represented by a sequence of just 2 things?
That's right, and you're already familiar with this fact. Because if we change the purple beads to 0s and the green beads to 1s, this itinerary is exactly our number written in binary.
Whoa, how does that work?
Let's start with a well-known fact. If we multiply a decimal number by 10, all we have to do is move the decimal point over 1 spot. Writing numbers in base 2 is less common, but it works the same way, except the digits decompose the number into powers of 2 rather than powers of 10. If we multiply a number expanded in base 2 by 2, all we have to do is move the binary point over 1 place.
Sure, I can see that.
Now with numbers on the circle, we ignore all of the digits in the 1's place or higher.
Since counting higher than 1 just brings us back to the same place.
And so doubling an angle is the same as removing the first digit of its binary expansion and moving all of the other digits over 1 space. We call this operation a shift. Now we can really start to connect this to dynamics. The binary expansion of a number is also an itinerary, each digit telling us which region it will visit after a certain number of iterations.
Given an angle expanded in binary, we can read off which region it's in using just the first digit, since the first digit of a binary expansion tells us if our number is greater than or less than 1/2. All the angles in the purple half of the circle have an itinerary that starts with 0.
Now you can see why I divided the circle from 1/2 to 0. If we combine this with the fact that doubling results in a shift of the binary expansion, you can see that after we double an angle, the new first digit is the second digit of the number that we started with.
So not only does the second digit indicate which region twice the angle is in, it also tells us which quadrant the angle started in. With 2 digits,
we've narrowed the location of our angle down to a quarter of the circle.
And the pattern keeps going. With each new digit we add, the binary expansion better approximates the exact location of our number, and the itinerary better describes the orbit.
Now that we know the binary expansion of a number is also an itinerary, I bet we can use that to answer questions about a number's orbit.
Yes! And this is the key to classifying the orbits of every point on the circle.
Right. A repeating or terminating orbit will give a repeating or terminating itinerary. And that's a repeating or terminating binary expansion. I already know that if a decimal expansion repeats or terminates, it must be a rational number. I would assume that this is true regardless of which base we're working with?
Right you are.
Now, we suppose there's an angle whose orbit never repeats or terminates. It would have a binary expansion that goes on forever without repeating, and a rational number.
Exactly. And you see how removing all of that specific information about the orbit actually helped us describe the numbers that we were looking for.
This is great. The categories we found earlier, terminating, periodic, and pre-periodic, they describe the orbits of rational angles. And irrational angles will have orbits which never terminate and never repeat. This new correspondence between an itinerary and the binary expansion brings other questions to my mind. Why does the decimal expansion of 1/4 terminate in all zeros, but 1/3 goes on forever? Or that weird pattern in the decimal expansions of fractions with denominator 7? Or why is 0.9 repeating the same as 1?
And I bet that this new insight will help you answer all of those ponderings.
But wait a minute. We got distracted. We were going to talk about the Mandelbrot set, but I don't think I've learned anything about the Mandelbrot set.
But now that you know all about the circle map, you have the tools for the first step in understanding the Mandelbrot set. And that's because squaring a complex number doubles the angle that it makes with the real axis.
Okay. So, well, how are we going to do it? How do we use the circle map to understand the Mandelbrot set?
To the void!